Hopefully, just go there. Why not? All right. So we were talking about bonding. Remember, there's kind of two types of bonding that we talked about. There's ionic bonding, which is between a metal and a non-metal. There we have a transfer of electrons. That's what creates our cation and our anion. And once again, it is that opposite attraction that holds that together. A reminder that in ionic bonding, we have no sharing of electrons. It's just simply the attraction between the positive ion and the negative ion that's going to hold that together. Now, molecular compounds or covalent compounds, that is between two nonmetals. And as we talked about, what happens when two nonmetals come together, they basically have the periodic trends that they both want to hang on to their electrons. They both would like to gain electrons. So the best that they could do is they will decide to share electrons. And that is what happens in a covalent bond is they will share electrons. Regardless of the type of bond, a reminder that basically the whole point of bonding is for everybody to achieve that kind of noble gas configuration in terms of their electrons, which will make them very, very stable. So I think where we kind of left off was the idea of the octet rule. And the octet rule means that everybody will basically keep making bonds until they have 8 valence electrons around them. 8 valence electrons will give them that same configuration as the noble gases and make for a stable bond. The one exception is hydrogen, as we talked about as well. Hydrogen can only have 2 electrons, and that's sometimes referred to as the duet rule. And hydrogen should never have any more than 2 electrons, because if you look on the periodic table, hydrogen just needs to get to helium here, basically to reach that kind of noble gas configuration and be stable. So once again, as I might have mentioned, with a lot of never, never, ever, ever, never, never put more than basically 1 line to a hydrogen, which represents 2 electrons, and that will max it out. It should never have dots around it, really. It should never have double bonds or triple bonds to hydrogen. It should only have 2. So in ionic bonding, the way we achieve that noble gas configuration, as we went over at the beginning there, is that they transfer electrons. So the metal will lose electrons and back up on the periodic table to the noble gas that comes right before it. And the nonmetal will gain those electrons and go forward on the periodic table to the noble gas that comes after it. And once again, in covalent bonding, by sharing those electrons, that's going to allow everybody to, again, to achieve that kind of noble gas configuration. Any questions on that stuff there? All right. So I think we were kind of skirting around it, but again, the octet rule is the main rule of bonding. And again, that means, like I said before, everybody will really continue to make bonds until they have 8 electrons around it. And as we'll talk about, sometimes in order to achieve that, it may require just a single bond to achieve that, may require a double bond to achieve that, it may require maybe a triple bond to achieve that. But they will continue to really do that until they have that electron configuration, which makes them really stable. And that's, again, the goal of it. Once again, hydrogen there only needs to go 1 step there on the periodic table to get to helium, which is 2 total electrons to become stable. Now, I think we might have touched upon this earlier on, but just to officially go over it, a single bond, like I said before, it may be all that's necessary for everybody to achieve that sort of noble gas configuration. A single bond is represented by 1 line, which represents 2 electrons or a pair of electrons. Remember that there's 2 different types of electrons that we talked about. There's all these guys here, which are dots. These are what are referred to as non-bonding electrons because they are not involved in bonds. And then obviously there's the electrons there that are involved in bonds, and those are what are referred to as bonding electrons. Sometimes in order to achieve that sort of noble gas configuration, you do need to make some double bonds. In the case of carbon dioxide, it actually needs to make not one, but it needs to make two double bonds. And you could show it with dots if you like. Or again, you could show it with lines to represent those bonding electrons. And once again, if we look here, oxygen on the left ends up with 4, 6, 8 electrons. Oxygen on the right, also through sharing with the carbon, will end up with 4, 6, 8 electrons. And our carbon in the middle, through sharing with both oxygens, will end up with also 8 electrons. And again, everybody in that compound has now, through sharing of electrons, in this case, again, requiring some double bonds to actually get that accomplished, has 8 electrons, going to make everybody really stable in this sort of bond. So again, 8, that magic sort of number there in terms of electrons, right? Now, sometimes you do need to go one step further than the double bond to get to 8 electrons. Sometimes you do need a triple bond to actually reach 8 electrons. And nitrogen, for example, there, as you can see, is an example where you actually do need a triple bond to achieve that. The nitrogen on the right here, 2 electrons there, 6 electrons being shared here in a triple bond, which can be represented by 3 lines, are 3 pairs of electrons, or 6 electrons, basically. By the way, a double bond, 2 lines, or 2 pairs of electrons. Nitrogen on the left there, 2 electrons there, and the 6 being shared in the middle, again allowing everybody to reach noble gas configuration. Same thing down here with acetylene. This carbon on the right has 2, 4, 6, and 8 electrons. Carbon on the left, same deal, 2, 4, 6, and 8. Hydrogen here by sharing 2 electrons. Hydrogen here by sharing 2 electrons. So once again, everybody hitting what they need to hit in terms of 8 electrons. As we'll talk about when we talk about drawing Lewis structures, you should probably not double bond or triple bond right out of the box. You should really kind of save double bonding and triple bonding for situations where maybe the octet rule is not met, and you want to kind of start with single bonds. And then if that doesn't kind of get everybody to the octet rule, then you want to kind of introduce double bonds. And if that doesn't fix it, then you want to kind of introduce triple bonds. It's usually the order at which you want to kind of draw these things. So we also talked about different types of covalent bonding and how electrons are going to be shared. And remember that we have an ionic bond where we have no sharing of electrons. We also have a polar covalent bond, which is between 2 nonmetals, and that's unequal sharing of electrons. That unequal sharing of electrons will result in sort of a charge to occur, partially positive on one side of the bond, partially negative on the other side of the bond, because of the unequal sharing of electrons. And we also have a nonpolar covalent bond, which is also between 2 nonmetals, and that's equal sharing of electrons. So in a nonpolar covalent bond, we have equal sharing of electrons, which means it's basically kind of like a neutral bond. There's not a side that's positive, there's not a side that's negative, because the electrons are being shared equally between the 2 atoms. It really creates kind of a neutral situation rather than in a polar covalent bond. So for example, HF, because the difference in electronegativity, the fluorine is going to pull the electrons closer to itself, and that's going to result in a partially negative charge on the fluorine, partially positive charge on the hydrogen, as opposed to if you just had 2 fluorines together, because they both have the same electronegativity values, they're both going to pull on the electrons equally. And the end result here is we're going to have equal sharing of electrons and really a neutral bond. There's not going to be a side that's more positive or more negative. Ionic bond, completely different, no sharing of electrons, and between a metal and a non-metal, so it's obviously something different as well. So what determines whether or not the electrons are going to be shared equally or unequally? Really, the big thing that helps us determine whether or not electrons are going to be shared or how they're going to be shared is electronegativity. Electronegativity is basically the ability of an atom to attract electrons towards itself. And on the periodic table, as you go up and to the right, it increases. As you go down and to the left, it decreases. Fluorine is the most electronegative atom that you could have on the periodic table. So let's take a look at how we could use this to sort of figure these things out. When we look at the difference in electronegativity, it helps us distinguish between how these electrons are going to be shared. So since electronegativity is that ability to bring electrons towards itself, when we have two hydrogens together, for example, what's going to happen is because hydrogen on each side is the same element, they will share the electrons equally. They both are going to have basically the same pull on those electrons. You could kind of think of it as like a tug of war, two people pulling on a rope, right? A little flag in the middle, if you will. So if you have the same person, basically twins on either side with the same strength, and they're both pulling the rope equally, basically that flag's not going to go anywhere, right? They're just going to kind of stay in the middle because they're going to kind of cancel each other out. And that's what happens in this case. When we have two of the same elements, they definitely have the same electronegativity values. So if we were to sort of look at how the electrons are distributed here, and if this red is sort of the electron distribution, we would kind of see a fairly equal distribution of electrons on each end of the hydrogen. And because of this, they're going to share electrons equally. And this type of situation, again, as I mentioned there, is what is known as a nonpolar covalent bond. Most people just call it a straight up nonpolar bond. It's implied that it's covalent, that they're going to be sharing electrons because they're both nonmetals. So if you have a nonpolar bond, you basically have equal sharing of electrons between the two atoms. Because of that equal sharing of electrons, as I mentioned earlier, you could kind of think of it as just being like a neutral bond. Again, there's like no positive side, no negative side to that bond. We've got nice equal kind of sharing of electrons between them. Same thing would happen with F2. Again, both of those fluorines would pull the electrons equally to each other. Again, if you think about a rope, they're both pulling the rope basically equally on opposite sides. We're going to get some nice even distribution that's going to happen, and that's going to create a nonpolar bond. So whenever you have equal sharing of electrons in a covalent bond, that is referred to as a nonpolar bond. And again, you can think of it as a neutral bond. There's no charges happening on that side. Now, what happens if we swap out a fluorine for a hydrogen? What happens in this case is we no longer have two elements that are the same, nor do we have two elements that are equal to each other in terms of their electronegativity. So because electronegativity increases as you go up and to the right, and fluorine is the most electronegative you could have, what's going to happen when fluorine and hydrogen get together is fluorine's going to kind of pull the rope a lot stronger than hydrogen is. And what that's going to happen here, as you kind of imagine, is hydrogen's going to go for a little ride here. It's going to hang onto the rope, but definitely that little flag is going to start moving closer towards the fluorine side. And if we look at the electron density that happens in that case, we would have a much greater amount of electrons hanging out over on the fluorine side than over here on the hydrogen side. And that does have consequences, as I just previewed a second ago. When that occurs, it actually creates charges within this bond. We end up with a partially negative charge. That's a delta negative there. And that basically means partially negative charged. And over here, where the electrons are sort of moving away, creates a partially positive charge on the hydrogen. This can also be represented with an arrow, which is sometimes referred to as a dipole arrow, heading in the direction of fluorine. These type of arrows always point to the more negative side of the bond, and the back end that makes kind of like a plus sign is always at the positive side of the bond when you kind of draw that dipole arrow. Now, why are these, for example, only partially positive charges and partially negative charges, and why are these not like full positive charges and full negative charges? Any ideas? So earlier I said, right, this is kind of like tug of war, right? My hydrogen's here, fluorine's pulling way hard, but hydrogen is still hanging on, yeah? So there is still some aspect of sharing that is happening here, but it is definitely not equal sharing of electrons, but the hydrogen is still hanging on for dear life. And because of that, we don't get a full transfer of electrons. So they're still able to share electrons even though it's unequal. So we don't get like we get in an ionic compound. In an ionic compound, when a metal and a nonmetal comes together, the metal just gives away its electrons. We get a full transfer of electrons from the metal to the nonmetal. And that's why we create ions in that situation. We create cations, which are positively charged, anions, which are negative charged. Here, because there's still an aspect of sharing, we create charges, but they're partial charges because they're still hanging on, even though not very much, but he's still hanging on the hydrogen there to the electron. He's not fully letting it go. Now, this is not a neutral sort of bond, and it does have a positive side of that bond and a negative side of that bond, which can be represented with that arrow as I pointed to. It also plays a very big role, as we'll talk about in some later chapters, in things like solubility, how molecules interact with other molecules, because something like this has a charge like that, a partially positive charge, partially negative charge. It allows it to interact well with other things that have charges very similar to that, things like water and stuff like that. So having a polar bond and this unequal sharing of electrons is a very important sort of aspect of molecules. Any questions on that there? This, by the way, is what is referred to as a polar covalent bond. And that is the unequal sharing of electrons. And once again, kind of like the nonpolar bond, most people just call this a polar bond. So if somebody says polar bond, it's the same thing as a polar covalent bond. And somebody says nonpolar bond, it's the same thing as a nonpolar covalent bond. Again, a lot of times people will leave the covalent part of the description out of it. So in a polar bond, we have unequal sharing of electrons, creates these partially positive sides to the bond, partially negative sides to the bond. And again, that plays some very important role in some stuff that we're going to talk about in some later chapters as well. And that's basically what we just talked about there. There's our arrow. Once again, arrow always points to the more negative side of the bond, more positive side on the other side in this case. The arrow should always point to the one that is more electronegative, and that will be the one that will be taking the electrons closer to itself. So to summarize sort of our three types of bonding that we talked about, we have ionic bonding, which is one end of the spectrum. And that again is between a metal and a nonmetal. And because of the metal and nonmetal being involved, where'd it go? We will get that transfer of electrons. And that is what's going to create those ions. So unlike the polar bond, we will get a complete transfer of electrons in this case, creating our cation, which again is positively charged, and our anion, the negatively charged. No sharing of electrons here. An example of that is sodium chloride. So sodium being a metal, chlorine being a nonmetal. The sodium is going to lay up its electron over to the chlorine, going to become positively charged. Chlorine is going to become negatively charged, and that's what's going to hold that together. On the other end of the extreme, we have a nonpolar bond, or a nonpolar covalent bond. And that is between two nonmetals. We have sharing of electrons, and we have equal sharing of electrons. An example of that would be anything like H2 that we talked about, or F2. Again, in each of these cases, we would expect the electrons to be shared equally, creating this nonpolar bond. In the middle of these two is a polar bond, and also between two nonmetals. And we have unequal sharing of electrons. And that creates this partially positive, partially negative that we just talked about. An example of that, obviously, is what we see there, and we just talked about, which is HF, right? So one end of the extreme, metal, non-metal, complete transfer of electrons. Other end of the extreme, two nonmetals, perfect, nice sharing of electrons, neutral bond. In the middle, two nonmetals, unequal sharing of electrons, not so unequal that the electrons get completely transferred, but not equal sharing of electrons in this case. Yeah. Yes, there will be, and it is possible. We'll talk about that in just a second. Actually, we'll come across some. And it is definitely possible. So for sure, if it's the same element, you got a nonpolar bond for sure. It is possible to have two different elements that will meet the sort of definition of nonpolar. So the good question on that is there is actually a difference, for example, in a sense, between a nonpolar bond, which is considered equal sharing of electrons, and something that people sometimes refer to as a pure covalent bond. Now, a pure covalent bond is still a nonpolar bond, but the difference between sort of a pure covalent bond and a nonpolar bond is this. In a pure covalent bond, it's like as perfect equal sharing of electrons as you get. Each of those examples there, the hydrogen H2 or the F2, would be considered a pure covalent bond. Because they both have the exact same sort of electronegativity value, that's going to create something that's going to give you this as perfect equal sharing as possible. Now, there's considered a nonpolar bond as well. One of the bonds that very commonly we will see is a bond between two different elements where the electronegativity value is not like perfectly zero difference. There's a slight little difference, but it is not considered enough to become a polar bond. It's still considered a nonpolar bond. So you definitely will come across some different elements that can create definitely a nonpolar bond. Is it a perfectly perfect pure covalent bond? It may not be, or it may actually be as well. There are different elements that can create a nice pure covalent bond as well based on their electronegativity. So how do we determine that? Let's actually talk about how we can actually determine whether or not we will hit a nonpolar bond, a polar bond, or really even an ionic bond. And really the main thing that we look at is electronegativity. And as I mentioned before, it is the ability of an atom to attract electrons towards itself. Once again, increasing as we go this way on the periodic table, with fluorine being the most, and decreasing in terms of electronegativity as you go down and to the left on the periodic table. It is based on electron affinity and ionization energy, a couple of trends we talked about in the previous chapter. Again, electron affinity is the ability, basically, our energy change that occurs when somebody gains electrons. So if you have high electron affinity, that means you typically like to gain electrons, and that increases as you go up and to the right on the periodic table. Ionization energy is the energy required to remove an electron. That also increases as you go up and to the right on the periodic table, which means as you go up and to the right on the periodic table, it gets harder and harder to remove electrons, and it typically doesn't happen because they much rather keep electrons than gain electrons. So fluorine, which is up and to the right, has high electron affinity and high ionization energy, and will have high electronegativity. Sodium, which is over here on the left of the periodic table, has low electron affinity and low ionization energy and low electronegativity. So how can we use this to help us decide in terms of, what type of bond we're going to get? There was a guy by the name of Pauling, and Pauling came up with actually a scale for electronegativity, actual electronegativity values. And his scale runs from 0 to 4. 4 is the most electronegative element you could have. That is also known as fluorine on the periodic table. And 0 is not so much electronegative, yeah? 0, not very much electronegative at all. 4 is the most electronegative you could have. You could calculate what is known as the change in electronegativity values. We'll call that delta En, change in electronegativity. You basically take the two elements involved in the bond, and all you do is subtract the two numbers. So you just subtract the two numbers. And basically, if you end up with a number that is anything from 0 to like 0.4, it is considered a nonpolar bond. If you subtract those two numbers and you end up with a number that's above 0.4, so like 0.5 to less than 2, it is going to be some type of polar bond, unequal sharing. This would obviously be equal sharing up here. And if you're above 2 when you subtract, it typically is an ionic bond. Now, to be honest with you, you absolutely positively don't need the electronegativity values to figure out ionic bond. The only thing you have to know to figure out an ionic bond is you have a metal and a non-metal. That's it. And as soon as you see a metal and non-metal, it's an ionic bond. You don't have to worry about electronegativity values or anything like that. And to be truthfully honest with you, there are a number of combinations when you make an ionic bond that will actually give you a value less than 2. So 2 is kind of a general ballpark number. So the best thing to do for ionic bonds is just go metal, non-metal, ionic. And that's exactly how you should identify that as being an ionic bond. Now for covalent bonding, where we're sharing electrons, you could use this. Now earlier the question was kind of about pure covalent and nonpolar. As you can see here, a difference of 0 in terms of electronegativity is that pure covalent bond, which is still a nonpolar bond. And that's like as perfect equal sharing as you could get. But as you can see on this scale, you could get upwards of 0.4 difference, which is really not perfect equal sharing of electrons, but is still considered not enough to be unequal, and is still considered a nonpolar and equal sharing of electrons. So there is sort of different degrees of nonpolar bond, even though they're all considered equal sharing of electrons, but there are some, there's like perfect equal sharing, and there's some like, okay, it's not like perfect, but it's close enough. We're going to call it equal sharing of electrons. But once you get to kind of that 0.5 or above, you now get into the range of unequal sharing of electrons basically are happening. So let's take a look at a table here. And this is a electronegativity table. Got this one here. Maybe it's better to look at. And you can see as you go up and to the right there, these are electronegativity values for things. And how you would use this table to help you decide is if we take a look at the 3 types of examples that we've been talking about, we take a look at sodium chloride. We take a look at HF. And we take a look at, we'll just do F2, why not? And if we wanted to use these values to help us decide if it's going to be polar, nonpolar, or ionic, what we do is go to the table here, and obviously these numbers would be provided for you if you needed them. You would go to the table, you would find sodium. Sodium is 0.9, so that's 0.9. Chlorine is 3. And basically all you're going to do is subtract the numbers. Take the bigger number from the smaller, so you get a positive number always. So if you take the difference in electronegativity, that's going to be 3 minus 0.9. That is a 2.1 difference. That 2.1 difference is above 2 and tells you that this is going to be an ionic bond because it's above 2. But really, you don't even need any of that because sodium is a metal, chlorine is a nonmetal right there. Just call it ionic at that point. You don't need any of that real calculation. But if you were going to do the calculation, that is how we determine it's ionic. If we come over here to fluorine, the two fluorines, fluorine here, which is the highest value you could have, is 4. This fluorine would be 4. If you took the difference there between 4 minus 4, that is 0. And that falls on the pattern of 0 to 0.4. That would be a nonpolar bond. And that's going to be equal sharing of electrons in this case. If you take a look at the hydrogen in the fluorine, hydrogen is 2.1. Fluorine is 4. You take the difference in electronegativity, big number minus small number, that is a 1.9 difference in terms of the electronegativity values. Remember that if you're anywhere from 0.5 to less than 2, and the difference in electronegativity, that is going to be a polar bond. And you can see at 1.9, like that hydrogen is like barely hanging on basically, right? Because you get to 2 and above, you're going to get a transfer of electrons. So this is very polar type bond. There's a very big difference in how those electrons are being shared. The fluorine is basically hogging them in this particular case. Question on how, yeah. I'm good with nonpolar. It is so just so we're clear, a pure covalent bond is a nonpolar bond, but sometimes people will classify that nonpolar bond as being pure covalent to indicate that's like perfect equal sharing. Because as you can see here, you can run up to like 0.4 and it will still be considered equal sharing and nonpolar. And sometimes people will just kind of use that to indicate that it's like as perfect as you could get. So nonpolar is good for anything like that. Now, if we take a look at a couple other examples here, like a carbon-hydrogen bond, a carbon-oxygen bond, a sulfur-oxygen bond, and maybe a carbon-sulfur bond here. And let's just say, for example, we wanted to use the difference in electronegativity to help us decide what type of bond we would have. So if we take a look here at our first one, which is carbon, carbon is 2.5 on the electronegativity scale. Hydrogen is 2.1. So if we take the difference between those two, 2.5 minus 2.1, that is a difference of 0.4. 0.4 means this is nonpolar, polar. This one's going to be nonpolar. It's the upper scale of nonpolar. It is also why the upper scale of nonpolar goes to 0.4 because carbon and hydrogens are the main bonds that we find in organic compounds, which we'll learn about later on in later chapters. And they are nonpolar molecules. So that's why we kind of cut off at 0.4. Now at 0.4, is the sharing here perfectly equal? The answer is truthfully is no. It's actually hedging a little bit towards the carbon is more electronegative. So the electrons are heading a little bit towards carbon, but again, not enough to be considered unequal sharing, still considered equal sharing in this case, and it would be a nonpolar bond in this particular case. If we take a look at the carbon and oxygen, carbon is again 2.5, oxygen is 3.5. So once again, if we did the difference in electronegativity, I'll do it right here. That's going to be 3.5 minus 2.5. That is 1. A difference of 1 should put it at what type of bond? This is going to be a polar bond, right? It's going to fall in that 0.5 to less than 2. So this would be a polar bond. By the way, if I drew that arrow, it should point to which element? Yeah, it should point towards the oxygen, which is more electronegative. So the electrons are heading in this direction towards the oxygen. I'll draw it underneath since I kind of butchered that there. And that means that the oxygen in this case is actually more negative, partially negative, and the carbon in this bond is more partially positive because of that unequal sharing of electrons that are happening in a particular bond. Any questions on that one there? Sulfur and oxygen, sulfur 2.5, oxygen still 3.5, I think. So that obviously is going to give us the same difference there of 1. So I won't write it again. So 3.5 minus 2.5 can give us 1, which means the sulfur and oxygen bond is also going to be polar. And the arrow should be pointing in this case towards oxygen, which is going to be more partially negative, right? Because it's going to be bringing those electrons towards itself and becoming negative. The sulfur in this case will become more positive because electrons are moving away from it, right? So it's got less electrons near it, become more positive. Lastly here, carbon, 2.5, and sulfur, 2.5. That's a difference in electronegativity of, I hope, 0, if I did that math right. That means this bond is a nonpolar bond. This is like perfect equal sharing of electrons. So to answer the earlier question, here are 2 examples where we have 2 different elements and they're both nonpolar. The carbon and the hydrogen at 0.4 is considered a nonpolar bond. Here, the carbon sulfur, also a nonpolar bond, actually has a pure covalent situation happening here, perfect equal sharing of electrons. Why does that happen with 2 different elements? It is what is known as the diagonal rule on the periodic table. If you look at the location of carbon and sulfur, they are diagonal of each other on the periodic table. Sulfur is further to the right, but carbon is further up, and they cancel out their differences. They're not right directly below and kind of over to the right diagonal. Also, nitrogen and chlorine, same deal. Yeah, chlorine is further to the right, but nitrogen is further up. So it is possible to have definitely 2 different elements that will actually share the electrons equally because of their relationship on the periodic table where they're located and their electronegativity values. Any questions on sort of how to use that? Lastly here, do you need the values in all cases? The answer is you don't need the values in all cases to figure this out. So if we look at something like 2 of the ones that we have up here, we looked at carbon and oxygen. When we look on the periodic table, carbon and oxygen is located in the same period, right? The same row. And since electronegativity increases as you go to the right, we see carbon is further to the left than oxygen. That tells you that the difference in electronegativity is going to be good enough to give you a polar bond. So if you're comparing somebody's in the same row, probably going to be a polar bond, and whichever one's further to the right will be the more electronegative atom. You don't even need numbers to figure that out. If you look at the other one, which is sulfur and oxygen is in the same group up and down on the periodic table. And when you look at electronegativity in the group, increases as you go up the group. So in this case, since oxygen is higher up in the group than sulfur, you know you're going to create a polar bond and oxygen should be more electronegative. You don't need the values to make that decision. So if you're ever comparing 2 elements on the periodic table in the same row, going to probably create a polar bond if they're both nonmetals, and the one further to the right would be the more electronegative. If you're comparing any 2 nonmetals in the same group, the one higher up in the group will be more electronegative and will create a polar bond. So in a lot of cases, you could just use the general trend and electronegativity without having to maybe need the numbers to kind of make that decision, and you should be in pretty good case steps there. Any questions on that? Okay. All right. So as we saw there, atoms with really big differences in electronegativity tend to form ionic compounds. This is also why when we get a metal on this side and a nonmetal together, there's such a big difference in electronegativity that the electrons just shoot off from the metal over to the nonmetal and they get transferred. That's why when we stay on the upper right of the periodic table with nonmetals and covalent bonding, None of them want to give up their electrons, so the best they could do is share. And as we can see there, sometimes they're not very nice in their sharing. They're not equally nice. Some may be pulling those electrons closer to themselves than others. And sometimes they will share nice with each other, depending on sort of their electronegativity values. All right. And that's a table from your book, again, with this kind of cutoffs that we just talked about. All right, so let's talk officially about how to draw Lewis structures for covalent bonding. And to draw Lewis structures for covalent bonding, I would say that if you want to draw correct structures, you definitely should follow these steps, and it should lead you to a proper structure. You definitely do not want to do it like piecework. You don't want to kind of do it like we did with ionic bonding earlier. You want to kind of think of it a little bit different. First off, the most important thing is to figure out how you put the thing together, so how it's arranged. To help you decide that, typically speaking, in the center atom is the least electronegative atom. So the least electronegative element should be in the middle. And for most things that you guys will draw, everybody else will just be attached to it. So kind of have somebody in the middle, and like everybody else is sort of attached to it. Two things that should never find themselves in the middle is hydrogen, because it should only have 2 electrons. So again, if you lay up hydrogen in the middle, it's going to have way more than 2 electrons. And fluorine should never be in the middle because it is the most electronegative element you could have. So it should always be on the outside. Probably the most important thing is number 2 there. You want to count up the total number of valence electrons in the entire molecule. Now, if you happen to have an ion, a polyatomic ion, it will have a charge. So you do have to take that into account. If your polyatomic ion has a negative charge, we add to the total number of electrons. Otherwise, you'll be short. If your polyatomic ion has I guess something to scratch that out. It should be positive charge on that second one. A positive charge. You're going to subtract that from your total. That number that you get is the most important number, because when you are all said and done, you got to hit that number exactly on the nose, your picture. You can't have any more electrons, can't have any less electrons. Once you've done that, what you want to do is go from the center atom to all the outside atoms, and basically all you want to do is make one single bond. I prefer lines, but if you want to use dots, you can. And remember that each of those lines represents how many electrons? 2. So you have that total number of valence electrons in your picture. Each line represents 2 electrons. You subtract off how many electrons you just drew. You will still have electrons left over at this point. All those leftover electrons should go on the outside atoms first in dots, pairs of dots. So you will fill up the outside atoms, like 2, 4, 6. That would fill that guy up because he now has a total of 8 electrons with the bonded electrons there. You would continue to fill up all the outside atoms until all the outside atoms have 8. The one exception would obviously be if the outside atom is hydrogen, right? You will not put dots on hydrogen because it will be done already once you put that first line on it. So no dots on hydrogen. Now, if you filled up all the outside atoms with dots and you still have electrons you need to put on your picture, then you go to the center atom and you pop it on the dots as well. So we work on the outside in. By the time you get to the center atom, you should be out of dots and electrons at that point. The last thing that you want to do is you want to make sure that everybody has met the octet rule. And if somebody has not met the octet rule, what you want to do is try a double bond first to fix it. And if a double bond doesn't work, then you could try a triple bond to fix it. And again, you want to kind of exhaust all your double bonds first before you move to triple bond. Remember, you do not want a double bond or triple bond right out of the box. You want to start with kind of single bonds when you do it. All right, so that's a lot of words. Let's go through one together here to see. All right, NF3. First thing we're going to do is figure out valence electrons. Remember, it equals the group number. So nitrogen is group 5, which means it has 5 valence electrons. There are 3 fluorines. Each fluorine is group 7, which means it has 7 electrons. That's a grand total of 26 valence electrons in my picture. I would say in most cases, if you have one element and 3 of some other element, the one element's in the middle. But nitrogen here should be in the middle because it's the least electronegative. We're going to go nitrogen in the middle, fluorine around. If you want, you can put the fluorine up on top there. I put it on the bottom. It really doesn't matter. I'm going to do one single bond to each outside one. 1, 2, and 3. At this point, I've used up how many electrons? 6 total. So if I take that from my total there, I still have 20 electrons I need to put on my picture in this case. I'm going to start on the outside one until everyone has 8. So 2, 4, 6, along with the line makes 8. 8, 10, 12, also with the line makes 8. 14, 16, 18. At this point, I just put on another 18 electrons. That means I still have 2 more to go. At this point, we then go to the center atom and we put it on as pairs of electrons. And that now gets me to no more electrons left in this case. Now that I've done that, I put all my 26 electrons on my picture. I want to make sure everybody has 8. So fluorine on the right, 2, 4, 6, 8. Fluorine down here, 2, 4, 6, 8. 2, 4, 6, 8. And nitrogen, 2, 4, 6, and 8. Everybody has 8 electrons. Everybody has met the octet. And we've only used 26 electrons. And this would be the proper structure here for NF3. Yeah. It's the number of valence electrons equals the group number. So nitrogen is group number 5 right here. So that's 5 valence electrons. And also that's where the 7 came from for the fluorine. Group number 7 has 7 valence electrons. So number of valence electrons again equals the group number. I think we definitely used that when we were doing ionic bonding earlier as well. Yeah. So other questions? The 3 is because in this compound, there's 3 fluorines. And each one is 7 electrons. Yeah. Well, we're running a rewind. All right, one more time in super slow motion. Here we go. Ready? All right, here we go. All right, we're going to calculate the number of valence electrons, which again equals the group number. So if we go to the periodic table, group number 5, there's nitrogen. So that is 5 valence electrons for the one nitrogen that is present. There are 3 fluorines. Go to periodic table, fluorine right there in group number 7. There are 3 fluorines. Each have 7 valence electrons. That's going to give us our 26 valence electrons for our picture. Once again, the least electronegative in this case is going to be nitrogen because it is further to the left, right? Fluorine is the most electronegative you could have. They're in the same row. So definitely fluorine shouldn't be in the middle. Plus, if you only have one element, like I said before, you want to probably put that guy in the middle, everybody else on the outside. So logical arrangement, nitrogen in the middle, fluorine on the outside. Now what we're going to do is just make a single bond to each of the outside ones from the middle. 1, 2, and 3. Each of those lines represents 2 electrons, right? So what I've just used now, which I think was the question where the 6 came from, I have now used 6 electrons on my 26 that I didn't put on my picture from those 3 lines. And now I have 20 more electrons that I need to put on my picture. Those are going to go on the outside atoms as pairs of electrons, dots. So I'm starting here on the right, 2, 4, and 6. I stop with 6 electrons on dots because this guy already has 2 electrons from the line, right? So the 2 electrons from the line is 2, plus my 6 I just put on gives it the magical number of 8, right? And that's where you want to stop, yeah. It doesn't really matter. You can start on any of the outside ones. I just kind of go that way, but it doesn't really matter. You could really start on any of them, yeah. All right, so then I'm going to come down here and give this guy the same treatment. 2, 4, 6, along with the line gives me 8 for that one. It cannot take any more electrons at this point. I got to go to the next outside one. and go 2, 4, 6 plus the line, going to give me 8. At this point, I've now filled up all the outside atoms, right? And I just put on dots on all the outside atoms, and I put on there, if you count all those dots, 2, 4, 6, 8, 10, 12, 14, 16, 18 dots. So if we take that off our remaining total, we still have 2 electrons that we need to put on there. Once you've filled up all the outside ones, now we go to the center, and it also goes on as dots. And now that is our last 2 electrons, no more to put on there. And now everybody we want to make sure has 8. So one more time, 2, 4, 6, 8 for that one. 2, 4, 6, 8 for that one. 2, 4, 6, 8 for that one. And 2, 4, 6, 8 for that one. Everybody has 8, has met the octet rule. And we have only 26 electrons if you count everything up there. Felt like a deja vu moment, but maybe it was just a slow-mo rewind. All right, let's take a 5-minute break. Yes? We'll continue on. All right, so we're talking about Lewis structures. And again, as I mentioned earlier, if you follow these sort of steps that we're talking about, it should really lead you to a pretty good structure. A lot of times people will kind of screw this up because they'll try to do it, like I said, maybe like in piecework. And they kind of take each individual element and they try to figure out, this guy's got 7, how many electrons it's got to kind of put it together with. And a lot of times when people kind of do it piece by piece, and they kind of think about electrons belonging to one element versus another, they oftentimes will end up with sort of too many electrons, not enough electrons, too many bonds. It's best to think about when you're drawing these for covalent compounds that those electrons don't necessarily belong to anybody, but your goal is to try to distribute them as evenly as possible to everybody that's involved, and that usually will lead you to a good structure. So let's take a look at another one here together. Let's say we wanted to draw the structure for nitrate. So once again, one of the first things you always want to do is figure out the total number of valence electrons. So once again, nitrogen. Let's try something that writes maybe. That'd be good. Try again. Try that. Nitrogen is group number 5 on the periodic table, which means it has 5 valence electrons. There are, again, in this case, 3 oxygens. So we're going to take 3 times 6. And the 6 comes from here because oxygen is group number 6 on the periodic table, which means it has 6 valence electrons. Now, on this particular one, it actually does have a charge. This is one of those polyatomic ions. It has a -1 charge. And negative charge means that somebody has gained electrons, right? That's how you become negative. So because of that negative charge, we have to make sure that we add that electron into our total. Otherwise, again, you're going to be short the number of electrons. So because it has a negative charge, you're going to add an electron. 19 and 5 is 24 valence electrons in this case. That, again, is how many electrons our picture has to have. And once again, in terms of the logical arrangement, like I said before, we have 1 nitrogen and 3 oxygens. There's probably a good chance the nitrogen's in the center and everybody else is attached to it. If you look at the periodic table, nitrogen and oxygen are in the same row. Oxygen is further to the right. That means oxygen is more electronegative. Nitrogen is least electronegative. And that also tells you it probably should be in the middle. So the arrangement here is just going to be like the last one. We're going to put nitrogen in the middle. We're going to put our oxygens on kind of 3 sides. Once again, you can put the oxygen there in the middle, on the bottom if you want, or top. It really doesn't matter where you put it. Just like last time, we're going to just make 1 single bond from the center to each of the outside atoms. So I'm going to put a bond there, and a bond there. At this point, we have now used, again, how many? 6. We're going to subtract off from our total. That's a lot there. 18, I hope, is left. So we have 18. I got a calculator. I should probably grab it. We have 18 electrons. Once again, we're going to put them on the outside ones as dots, pairs of dots, not individual dots, but pairs of dots. And we're going to fill up all the outside ones with 8. Obviously, we don't have hydrogen here. We don't have to worry about that. So we're going to go 2, 4, and 6. Once again, this oxygen has the line coming in. which means it has 2 electrons already. So that's going to give it 8 total in its field. We're going to go 2, 4, and 6 here, which also with the line will give the oxygen up on top 8. And 2, 4, and 6 there with the oxygen line there will give it 8. And that's another 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons at this point. And I have now used up all the electrons that I have available to me. Once I do that, the last thing I want to do is make sure everybody has met the octet rule. Does everybody have 8 electrons here? No, nitrogen's a little short. Nitrogen only has 2, 4, and 6 electrons. All the outside ones do have 8, so all the oxygens, if you go around, have 8 electrons on them. So this is a situation where we have not met the octet rule, so we want to fix it. So can I fix it by simply just putting some dots there? What is wrong with that? It now has how many total electrons? 26, which is more than it should have. So you cannot just put electrons on it to fix it, even though you might want to because it seems like an easy move, right? But it's not correct because it'll give you, again, too many electrons. I'm going to try not to take out the line. Maybe. Or not. Maybe I'll just leave it. Don't play with it. All right, so this is a situation where we have not met the octet rule, so we want to make a double bond to try to fix it. That's kind of our first option, is to make a double bond. In this particular case, every single oxygen, they're identical to each other. So you can make a double bond at any oxygen you would like. So when we make a double bond, that's obviously another line. Can I just put another line in there? I cannot, for the exact same reason. I now have 26 electrons. The oxygen up on top has how many around it now? 2, 4, 6, 8, 10. Too many, yeah? So more than 8. So when we go to make a double bond, and by the way, if you need to make a triple bond as well, what we actually are going to be doing is we need to actually grab a pair of electron dots, bring them in so we can make a double bond. So if I want to grab a pair of electrons from there, I'm going to bring those electrons in to make the double bond. And when I do that, I will end up now with a double bonded oxygen up on top. I will still have my single bonded oxygen to the right. I will also still have my single bonded oxygen to the left. And because we're happy students here, we'll put a little bracket around it with a minus sign. Because something with it makes it a little fancy. But now what we have done is we have now fixed nitrogen's problem, because if we look at nitrogen, it now has 2, 4, 6, 8 electrons, so it's good. The oxygen up on top, 2, 4, 6, 8 electrons, it's still good. These guys are still good, 2, 4, 6, 8, 2, 4, 6, 8. Everybody now has 8 valence electrons. There is still a grand total of just 24 electrons on that picture. That would be the structure there for nitrate. Any questions on that? Now, could you have double bonded, like I said, to the right or left? You absolutely could have. So if you chose to double bond there to the right, you would have ended up with a picture that looks something like this, with the double bond on the right, single bond up here on the top and left. And again, a little bracket around it. Or you could have double bonded there to the left-hand side, where you could have had a double bond on that oxygen. All 3 of these structures are actually related to each other. These are what are known as resident structures. And resident structures basically happen when you have this situation. We had multiple places where we could have done the double bond, so we could draw another Lewis structure to represent that. And the truth reason why you could do that is when you make the double bond, those electrons are what are known as being delocalized, which means they're not stuck to one particular atom. So at any given point in time, those double bonded electrons that you brought in to make the double bond could be over here at this atom, They could then be up there at top of that atom, or they could be to the guy to the right. So they are technically moving around. And that's why you could draw three different structures for it, because the true structure is probably somewhere between all three of those. If you were asked to draw the Lewis structure for nitrate, you could lay up any one of the three pictures there, and they would all be correct. If you're asked to draw the resin structure, which you probably will not be asked to draw in this class, you would draw all three with arrows. So, any questions on that there? All right. Well, I did one. You do one. Yes. All right. Draw the Lewis structure for carbonate. Here we go. So again, we're going to get our valence electrons. So going to the periodic table. Go to the periodic table. We got carbon at group number 4. That's 4 valence electrons for the carbon. There are 3 oxygens. Each is group number 6 on the periodic table. And here we have a -2 charge for this ion. That means it has gained 2 electrons. You have to add that to your count over here. Otherwise, you're going to be, let me choose a better word there than I was going to say. You're not going to be right. That seems like the nicer word to say there. Insert any other word you think is appropriate. 18 plus 2 is 20, plus 4 more is 24. Oh boy. There we go. Spend a day. Obviously here, looking at carbon and oxygen on the periodic table, there's only one carbon, probably could go in the center. But just to reinforce that, oxygen is further to the right, which means oxygen is more electronegative. Carbon is least electronegative. So once again, we're going to place our carbon in the center. We're going to just put our oxygens around. And we're going to do our normal single bond to each of them. That is going to, again, give us 6 electrons here, 2 for each line. That, again, I got it better this time, I think 18. I maybe did that quicker this time, not too bad. We're going to fill up our outside just like before. So 2, 4, 6, 8, 10, 12, 14, 16, 18. At that point, I have no more electrons to give. Is everybody okay here? No. I'll ask again. Is everybody okay here? Because the carbon. The carbon is not okay. Don't let carbon be not okay here today. Carbon only has how many electrons? 6. And it's not called the, I'm not gonna say it because I'm gonna say something bad. It is called the octet rule, which means it needs 8 electrons, and it obviously does not have 8 electrons there. So this is a situation where, again, we need to make a double bond, right? Doesn't matter which one I take it from. The important thing is, right, we need to move those electrons in to do that. So I'm going to go from the top one here. We're going to take those electrons, bring them in. That's going to put our double bond up there on top. Everything else is going to stay exactly the same. So these guys will still be single bonded. Put a little bracket around it. Put a -2 on the outside to make it look fancy. And now, again, we have 8 electrons for everybody. The carbon, by making that double bond, now has 2, 4, 6, 8 electrons. Each of the oxygens that are single bonded have 2, 4, 6, 8 electrons. And our double bonded guy, 2, 4, 6, and 8 electrons. Again, we have only 24 electrons in this picture. Yes. Question on that one. Yeah. Yeah, you can draw some resonance structures for this, and basically the only difference is you just maybe make the double bond to the right versus the top, or make it to the left versus the top. Again, you just basically move the double bond to the different locations. Other questions on that there? All right, let's take a look at, why don't you draw SO2? Why don't you draw NH4 plus? Why don't you draw CO2? Why don't you draw NH3? Not like that one? Sorry. How about N2? It's just like 2 things. How bad could it be? I don't know. All right. Take a few moments there. Draw up some Lewis structures. Make sure everybody has 8, yeah? Take a look at it so we can go through these and you can see them here. See how you've been doing. All right. So we'll start with the first one here. We're going to get our valence electrons. So sulfur is group number 6 on the periodic table. There are 2 oxygens. Each are group 6 as well, I believe. So that is, math is really strong today for myself. 18 electrons. I can grab that calculator soon. All right. So again, we're taking a look at sulfur and oxygen. They're in the same group, right? That means oxygen is further up, so that is more electronegative than sulfur. Plus, you only have one sulfur. Put the one guy in the middle, probably in most cases. So I'm going to put sulfur in the middle. I'm going to throw me some oxygens to either side. I'm going right and left. You technically go up and down if you want. It doesn't really matter. I'm going to do our normal 1 bond to each, right? In this case, I have now used up how many? 4 electrons, right? 2 for each of those lines. That is 14 to go. I'm going to put them on the outsides as dots. So 2, 4, 6, 8, 10, and 12. At this point, I have now put on my picture 16 total electrons, but I only put an additional 12. I still got 2 more to go. They also go to the center atom, and they also go as dots as well. So that's how those dots get there, by the way. It is not double bonded on both sides, which people like to draw for this particular one. At this point, we now want to make sure, like normal, that everybody has met the octet rule. Has everybody met the octet rule in this case? No. Which one is short? It is sulfur. The one in the middle only has 6, right? It's got 2, 4, and 6 electrons, right? So again, we can make a double bond. Doesn't matter which way I make my double bond from, which side. It doesn't. So you could make it to the left if you like, or you can make it to the right. You would have some resonance structures here. I'm just going to grab it from the right. So I'm going to take these electrons and move them in. That's going to give me still my double bond, my 2 electrons up on top, my double bond to the right, and my single bond over here. Now the sulfur in the middle has 8 electrons, right? 2, 4, 6, and 8. All the outside oxygens have 8 as well. We still have only 18 electrons. And again, this is another one you could draw a resonance structure and just make the double bond on the other side. Any questions on that one there? Yeah. Why do we subtract? Yeah, so you don't have to necessarily do that. I'm just keeping track. We have 18 total electrons we have to put on the picture. So the 4 came from our very first 2 lines we drew. So each line represents 2 electrons. So that's 4. So what we have left after we draw that first single bond is we have to still have 14 electrons to put on it and stuff. Yeah. Other questions? All right. Coming over here to NH4 plus. Nitrogen, group number 5. Hydrogen is 1 valence electron, and there are 4 of them. Right? What do I do with the plus? Add or subtract? Right, because plus means that we lost electrons. So here we need to subtract 1. And that is 8 valence electrons. Obviously here, who should go in the middle? Nitrogen, right? Because hydrogen should never find itself in the middle, right? So nitrogen, and since there's 4 sides, I'm going to put a hydrogen on each side. I'm going to make a single bond from the center atom to each outside atom. How many electrons have I used? 8. I got nothing left, right? So now I need to make sure everybody's good. Is everybody good here? They are, because all the hydrogens only need how many? 2. And by having just 1 line to them, they all have 2. And my nitrogen in the middle, 2, 4, 6, and 8. There it is. Yeah. So any questions on that one there? All right. Coming over here, a little CO2 action. Carbon, group 4. 2 oxygens, group 6. I know. I'm almost done here. That's 12 and 4 is 16. All right, so between carbon and oxygen, same row on the periodic table. Oxygen again further to the right. Plus, we only have 1 carbon as well, right? Least electronegative and only 1 of them. We're going to put it in the center, oxygen on either side. Same deal. We're going to do a single bond to each. That's now going to use up 4 electrons, right? 2 for each. If we want to subtract off, that leaves us 12 to go. On the outside here, 2, 4, 6, 8, 10, and 12. At this point, I have now put up all 16 electrons Is everybody good in this case? No. Who is not good? Carbon is well short. It only has 4 electrons, right? It needs 8. So here again, we can make a double bond. Doesn't matter which way. Does it? So we're going to take a pair of electrons and bring it in. That's going to now give us a double bond to the left here and a single bond to the right. Did that fix the problem in this case? Did not, but it got better, right? Because now carbon has 6. Now, you may be tempted to go, can I lay me up a triple bond? The answer is yes, but you probably shouldn't because it gives you a terrible picture. But the reason we don't want to do triple bond yet is because I still have the ability to make a double bond on the other side, yeah? So you kind of want to use up all your abilities of double bonds if that first one doesn't fix it, and then go on to triple. So we're going to do the same thing. We're just going to take a pair of electrons and bring it in on the other side. And now we're going to double bond both sides here. Oops. And now what we're looking at is carbon in the middle there with 8 electrons. Each oxygen will also have 8, and we still have only 16 electrons. So again, if you do have more than one option to make that double bond and the first double bond didn't fix the problem, you really do want to kind of exhaust your double bond opportunity before you move to triple. Any questions on that one there? All right, 2 more to go here for the season. No, I'm just kidding. I wish the semester's not over yet. It's wishful thinking. All right, nitrogen, group 5 still. This was the one that got when I wrote it. Hydrogen 1 there. And let's see how bad it is. 8 valence electrons, right? Some bad math maybe. All right, nitrogen is going to go in the center because we know, again, hydrogen cannot. So 1 bond there, 1 bond there, 1 bond there. That is a grand total of how many electrons? 6. Got 2 more to go. Can I put any dots on any of those hydrogens? Oh, that's the right answer. Thank you. So that means you can't put any dots on the outside. So next place we go is inside here. And we pop a couple of dots right there. That is now 8 electrons distributed. Nitrogen has 8. Each of the hydrogens have 2. That is it there. Right there, yeah. Any questions on that one? Lastly, a little N2 action here. That is 2 times 5. For each nitrogen, that is 10 valence electrons. There really is no central atom here because there's only 2 atoms, so you can't have a central atom without 3. So just going to put them side by side, and you can follow the same procedure. So I'm just going to put a single bond like normal. That is going to use up 2 electrons. Gives me 8 to go, just like normal. We're going to put them on the outside. So 2, 4, 6, and 8. At that point, that is all the electrons. Are both nitrogens good? No, the one on the right's good. It's got 8, but the one on the left only has 4. So we follow our same rule here, which is we're going to try to fix it with a double bond. So we're going to take some electrons from here. We're going to bring them in to make a double bond. And now that will give you something that looks like this. Did that fix the problem? Did not. It got it better. Nitrogen on the left now has 6. Guy on the right still has 8. There is no other place we can make a double bond at this point, right? So the next thing we need to go to is a triple bond. So we do the triple bond the exact same way. We got to take another pair of electrons and bring them in. And now a little triple bond action in the middle. Now we are good, right? Each nitrogen has 8 around it and a grand total of 10 electrons in this case. So again, if you follow those sort of